Hello and welcome to this 5-minute short, and this time we're going to look at how we can size a relief device using this direct integral method. So the direct integral method is a universal sizing method. You could use this for all your relief device sizing. Normally though, we'd stick with the normal API 520 ones, but where we use this, if I can go back to our API 520 calculation, if you've got this Z here, so if your Z's lower than 0.8, higher than 1.1, we're stepping away from this assumption of ideality. So we need a more accurate method, a more precise way of calculating our relief device area. And you'll meet that in things if like a supercritical relief. Again, this is kind of like the area where you'd start to use this kind of method. Now we're just going to use it on our toluene example, and it works perfectly fine for this. Say in reality, it's a bit of a sledgehammer to crack a nut. So where we're finding this, if we go to this size estimation up here, we've got API 520 vapor direct integration. That's the sheet you're seeing now. There's another one here. It says API 520 two-phase direct integration. Lo and behold, it looks exceptionally similar. This method works for two-phase flow, single-phase flow, gases, liquids. API uses it twice in the appendix for Appendix B and Appendix C, so why can't we? But they're fundamentally the same method. So this top bit here really is just for information. So we've got a fluid as toluene, 6-bar gauge, we've got our design pressure, our accumulation, we've got our toluene temperature that we had before, but that's just coming direct from our physical properties. So there's a video on how we generated those. We're going down to atmosphere, and then our required flow rate is this 1500 kilograms an hour that we got from our fire case, which is over here. So hopefully, you watch the other videos, you will find how to do those bits. Now with this method, really the fun bit comes down the bottom of the sheet. So I'm going to scroll down, and you've got this at the bottom of the sheet, this table of data. And what we need to do is we need to do an isentropic flash from our relieving pressure all the way down to our ultimate discharge pressure. So we're going to bring in FizzPack, because FizzPack is going to be our friend at this point. So you can see I've got this one set up here. I've got toluene as my components, and I'm going to go into specification. So normally we use vapor liquid effluent. That's the one most people use. We start playing about trying to get physical properties. In this case, we're going to go all the way out to the bottom to our vapor liquid mass flux. So our temperature, we're going to do 201 degrees C, and then we're going to do a range. So we've got 6.6 bar gauge down to atmosphere, and then we want 101 points. Why 101 points? API asks for 1% intervals, or suggests 1% intervals. It doesn't have to be, it can be more, it can be less, but 1% interval seems fairly sensible. And if you count them up, that equals 101 points, which the FizzPack defaults to. So if I close that, and I'm going to press calculate, so FizzPack is going to twirl away and come up with a table of data. So what we're looking for here, we're going to do an isentropic flash, so we're keeping entropy constant. These 1% intervals is going to give a table of data for our pressures. It'll tell us our temperatures. We're not that bothered about our temperatures, but what it'll also tell us is our densities or specific volumes. And it's that density, that pressure density, specific volume data that we need for the table, because that's what it uses in the calculation. And it will use that data. It will do an integral, and we'll see this in a minute when we look at the data, throw it into an equation, and what it will basically do is draw a nice pretty graph, and we'll find a peak, a maximum mass flux. And that's what we're going for, mass flux from our face. It'll tell us our maximum mass flux, and that's the number we need. That's the number we can use for our device sizing. That's where we're getting choking. So we can see FizzPack said 100%. If I bring this over here, here we go to our table of data. It's these two columns that we need, our stream pressure and our stream density. So if I right click, I can do Copy select results, no headers. So that's just going to give me the data, just the numbers. So I can close all that. And then I can paste that in there. And we've got some numbers. Now we need to be a little bit careful. What units? So I was in bar gauge. So let's put that into bar gauge. I was using density. If you were using specific volume, it's just 1 over density. You could change it there. That's going to give you a very strange looking graph. So we'll stick with density. And then we get this nice pleasing curve. We've got our maximum up here somewhere. And of course, we can use Excel functionality to determine that for you. It even tells you roughly where it is, 0.46. So we take that mass flux. So that mass flux, it's going to be suddenly filled out through here. And we're most of the way through our calculation now. So our discharge coefficient, so it defaults to 0.85 on the sheet. And that's because where you get into two-phase flow, API 520 recommends using a preliminary sizing KD of 0.85, not 0.975. So we've defaulted it to 0.85. We're just doing a normal vapor, so I'm going to put it back to 0.975, make it similar to what we had before. There is no KB, we've got balanced bellow valve. We're going to have a KC, because we had the KC before. We haven't got a KV, there's no viscosity correction factor. But if you're doing a purely liquid sizing case, you might need to think about your KVs just as you would do otherwise. But again, it's just a pure liquid case, just use API, much simpler. So we've got an area, and then we're going to pick something in here. So again, we look at this table. F would be too small, 198, but a G, 325 is big enough. And then again, it gives us our rated capacity and our actual capacity. Now you will get a slightly different number if we go back to our sizing calculation. So we got a KDA of 201. If we scroll down here, you got a KDA of 190. So you do get a little bit of a difference. Normally in relief device sizing, is it a big difference? No, you're going to look to the next size. Whether these two methods are within 10 square millimeters or not doesn't really make a massive difference. But actually in this case, if you look at the previous one, we would just have been an F. Now we're definitely a G. And then we did say last time, probably worth going up to a G. So it can make a little bit of difference. And, this is just some of the assumptions behind the method. So toluene has got quite a low compressibility. If I go back here, we're at 0.85. We are getting away from IGLT, so that might well be the reason. But not trying to worry people. 0.85, you could use that method absolutely fine. It's within the standards. Something that close, 8 square millimeters, we'd go up a size as a general kind of rule. But there we go. But fundamentally, how do we calculate and use this direct integral method? It's that simple in many ways. It looks horrible in the standard, but as long as we get the phys pops right, we believe the physical properties, we can paste it in, and it's a relatively simple method to use. Thank you very much.